So, today we're joined by Brian and Raphael at Make IT conference in Portorož. Brian and Raphael, how are you?
Good, thank you.
We've just finished the workshop. First of all, I would like to congratulate you and say the workshop on vector embeddings was really nice. And just for the audience, briefly explain what was it about.
Take it, Raphael.
Yeah, so basically, I think that the core idea we wanted to teach the audience with this workshop is that they don't have to call LLMs for every single task that they want to do. Because right now, people are starting experimenting with LLMs and you have many different, let's say, applications to it. For example, one of them is classification. So you can have like a text and you can ask the LLM what this text is about, for example. But if you know beforehand that you want to classify only texts that are about a certain topic, such as artificial intelligence, you don't need to use the LLM to do so. And actually, by doing so, by using an LLM, you're wasting money because you have to pay for that in terms of tokens, basically, which might become expensive very easily. You're wasting on time because LLMs, they take a little bit longer to respond, especially depending on the model that you're using. And finally, you're wasting on Earth resources, right? Because you need a lot of GPUs to generate responses from LLMs.
And electricity.
And electricity. So there's...
And water.
And water, exactly. So there's this whole debate around the use of LLMs. I'm not advocating against the use it. It's not that, but maybe minimizing by using different techniques that might be more efficient, basically.
And using the right tool for the right occasion.
Exactly. So if you have like, what people are doing now is that they're using a driller, is that how you say it, for drilling, for every task, when they could use a screwdriver, for example, which would be cheaper and maybe even more efficient depending on the use case.
Okay, so getting into the workshop, what is alternative to classifiers?
So the alternative to LLMs actually is vector databases. In other words, vector similarity search. In this specific use case, for example, what we're doing is we're going to the LLM and you're asking, hey, regarding this text, is this about artificial intelligence, for example, or another? Is this about American politics? Is this about Brazilian football? You can define what you want to do, right? But if you want to use a vector database and vector similarity search, do the same thing. What you can do instead is come up with a bunch of references. And in the workshop, we used only about 100 references. So you can see that it doesn't have to be like 500,000. It can be just a few hundred. In this case, we used 104 references that were synthetic generated. So basically, I went to ChatGPT and I asked ChatGPT to, hey, create me 100 references of posts from Twitter or Blue Sky that are about artificial intelligence. And then what I did was I got this posts, I vectorized them, I turned them into embeddings, I stored them in the vector database, which was Redis in this case. And then whenever I got a new text, what I was going to do is I was going to vectorize this text as well. And then I was going to compare the vector of this text to all the references that were stored inside of the database. And if the vectors that were inside of the database were similar enough to the one that I had just vectorized, it would mean that the text was about the same topic. See, and all of that in a much faster and efficient way than actually using the LLM, and still with an output that is just as accurate as the LLM could give, you see.
It's a general concept that everybody should take into account. It's that LLMs are a general purpose computing engine nowadays, and everybody's using them that way to basically do everything. One thing that we always had for many years, it's really efficient classification models, for example. But nowadays, we're basically telling LLMs, it's like, hey, classify this random set of things. And we're relying on that parametric world knowledge for it to be able to do that. But it's typically inefficient. So there's smaller models. There's actually all the techniques that don't require AI at all. That have been proven over the years. So it's a combination of those things, but using the LLM in the right places to sometimes just enhance the behavior of those. That it's the correct way to actually use these things. Right now, we're really basically seeing them as engines and then basically just bolting out wheels around this in a chassis. But they're not. They're more like a carburetor or a small part of the engine that can optimize other parts, but it's not the end game for everything.
Nice. I think that's a great segue for you to explain me what is vectorized text and what are vector databases, and how do we use vector databases to actually classify some text.
Yeah, so vector databases have been around for longer than I have been alive. And the difference is that now we have models that can create those vectors. Before, vectors could be, for example, one-hot encoding, which you basically take different features of something and you turn those features into numbers, and then you put all those numbers together into an array, and then you use a vector database or just the cosine similarity algorithm to basically find how related some of those vectors are. And what happens in let's say you have 10 dimensions, so you have a 10-dimensional space, and you have vectors in that space. If you could visualize it, you could see that similar things, based on the model that we're used to encode them, would basically be in the general vicinity. So they will form clusters. So typically around a topic or a specific set of keywords. But typically with new models, it's about the meaning of what that text represents. So we basically take these models that used to be classification models in most cases. I'm going to use the vision analogy because it's an easier one to understand. But you probably all seen the neural networks where you basically give it a picture of a cat, and then at the bottom it will tell you, yes, this is a cat, or no, it's not a cat. So that would be binary classification, yes or no. But you also have networks where you have multiple classes. And the classes could be cat, dog, different animals, or it could be general objects like something like YOLO, where it can recognize shoes, a car, a building. So it's a really strange combination of things. Yeah. So to create embeddings, typically, and this was basically a stroke of luck. Somebody decided, okay, since we're classifying things, somewhere inside of this network, there's going to be a representation of this, that it's numeric, that we can use, because these networks are basically a set of weights in layers. And what they discover is that we can basically not do the classification at the end and just grab one of the intermediate layers and look at those numbers and then see how they compare to other numbers for similar elements that we're classifying or different elements. And based on the specific model, they find that basically we can compare these things in a very efficient way, because it becomes a matrix operations, which basically computers are really good at, and specifically GPUs are really good at integer matrix operations. Therefore, made all these things very, very fast, which allowed us to do things like self-driving, be able to recognize objects from a moving vehicle in real time. And then that was combined with other techniques taken into the world of NLP, or natural language processing. And now we have things like the transformer model, which basically it's what most of the LLMs that we use today are based on, which do the similar thing with text. Take text, turn it into a set of numbers by grabbing a specific set of those numbers from one of those neural networks. And we're seeing the results of it. It's pretty amazing, pretty incredible. But again, it's a double-edged sword. A lot of power, but also a lot of resource consumption, delays. We're talking about seconds, while something from a vector database could be milliseconds or sometimes sub-millisecond.
Yes.
Nice.
Yes. And I think that if you want to put it in a nutshell, actually a vector is a numerical representation, like a meaningful numerical representation of some data. So if you're talking about text, for example, how can you represent that as numbers? If we're talking about mass or temperature, you can easily represent those as numbers. But if you're talking about text, how can you do the same? And that's where embedding models come into place, because they're able to turn this unstructured data, such as text or audio or images, into numerical meaningful vectors that you can then store in a vector database that can then efficiently, in this vector multidimensional space. So you can imagine, for example, a 3-dimensional space where you have these vectors scattered all up in this place, basically, and you have one single one that you want to compare to all the others, and you want to find out, okay, what's the most similar vector, or what's the closest vector to this one in this multidimensional vector space. And that's basically vector similarity search, very roughly speaking.
Let's say I have 2 strings. One is tiny home and one is small house, which not equal. So if I would put them in vector database, they should map to a similar vector.
Correct.
Yes.
And the discovery that made that possible, it's called attention. So basically, you look at, for example, a word, a noun, verb, or something like that, and you look at the surrounding words, and you change how you evaluate that word based on its context. So, and there was a paper that basically started the whole thing. Attention is all you need. Then that spawned the Transformers model paper. And but that concept of basically looking back and forward and see what's around that word allowed them to create a better vectors for a sentence or a fragment of text. And they just happen to basically semantically map to the same multidimensional space. And if you put them in a vector database, now you can find all the ones that are close together. So
yeah.
So the main application of vector databases is searching, and or give us a couple of more examples where vector databases might be very useful.
Yeah, so this first one that you just described was semantic classification, but you can do also semantic caching, right? So as you said, have tiny home and you have, what was the word? Small house.
Small house.
Small house, right? One that I like to talk about is actually about the talk that I'm going to deliver on Friday. That I use the data from the Apollo 11 mission, the transcriptions of the mission, and I do vector similarity search on that, so you can learn more about what happened in space with the crew and also with the mission control back on Earth. But the example that I give is that some people are going to ask the chatbot, for example, how did they go to the toilet? And other people are going to ask, oh, how did they go to the bathroom? Those are the same questions, right? So you're going to get this question, you're going to get the enriched data that you're going to stuff into the prompt, and you're going to send it to the LLM, and the LLM is going to take money, time, and energy to generate the response, and then you're going to return this response to the user, right? But what you can do instead, you can do that the first time, but then you can also get this response and put it in a vector database alongside the query or the message sent by the user. But in this case, you want to vectorize the message so that if somebody asks something similar in the future, instead of going to the LLM all over again, you can go to your semantic cache and see, has something similar to this being asked before? And if it's similar enough, like tiny house or small home or something like that, instead of going to the LLM and wasting resource and time, you can actually go to the cache, which is Redis in this case, and return the response from there.
Well, and you can take it a step further. So imagine you have this cache. When people ask a question, you get the answer from the LLM the first time, and you put it in the cache. And then people keep on asking similar questions. So now you can keep count of how many times that specific semantic question has been asked. And now have statistics that is a hotkey in your cache. So you could make the answer better. On the background, you can basically go and find and use maybe different LLMs and say, here is the initial answer that we got from LLM X. Now let's use a more expensive one to create a better answer, or summarize it, or add extra links and references to it. So now when people hit that cache, they're going to get a better quality answer without hitting the LLM again, in fractions of a second compared to the LLM time. So.
Amazing. I'm curious, what's vector database role in retrieval-augmented generation, or RAG? So I've heard this term a lot of times.
Yes.
Never truly explained that well.
Yeah.
So
yeah.
I'm very curious to hear from you.
Yeah. So I can talk. We've been doing basically RAG day in and day out. So RAG, it's retrieval-augmented generation. The R, the retrieval part, it's basically getting information that is going to help you ask a better question to an LLM. In this case, the retrieval could be from a relational database, from a search engine, from a tool that hits Google, for example, to get answers and put that as part of the prompt that you're going to send. Now, in professional environments or enterprise environments, you typically would have a system that has questions about a specific topic, a specific domain of expertise, and to augment that data.
That is private, right?
Yeah. Exactly. So, for example, let's say it's a financial institution and you have all kinds of documents that nobody outside the company should be able to see, but also only certain people inside the company should see. So if I am, let's say, a bank teller, and I go ask this expert system in a company, a RAG application, some question, the retrieval has to be smart enough to know, okay, this is the user that's asking the question. These are the permissions that this user has. These are the places where I can get data about this. And then get that data, potentially summarize it, clean it up, and then make it part of the prompt. So in RAG, typically you have a prompt that is consisted of typically the rewritten user query, because humans don't ask questions the right way that would be optimal for a system. So sometimes a poorly phrased question would have to be rearranged so it's better for the system. Then you also have to retrieve enough information to give it context. So for example, if it's a financial institution, here's like basically, I don't know, the salary tables in where you land in this. And if you're asking like, when should I expect my next promotion, things like that. So you have to have that context specific to the company. And LLMs have knowledge that it's global parametric knowledge. So basically knowledge from a lot of different sources like, Wikipedia, Reddit, crawling the web illegally, all kinds of things that, potentially, tweets and things of that sort. And in there, you're going to get a combination of truthful data, lies, conspiracy theories. So everything that it's good and bad about humanity, it's part of the LLM training data set. So RAG, the R in RAG, allows you to find data that is better grounded on the topic, on the specific domain, company that you're trying to answer a question for, and make the prompt that goes to the LLM better.
So it's in a way approach to provide more context to the LLM for the data that it has not been trained on.
Exactly. And that retrieval part is part of the information retrieval world in computer science and in informatics. And that's also been around for longer than all of us have been alive. So there's a lot of complex techniques to basically do good information retrieval. And in the modern world of RAG, we're just touching the top of the iceberg in terms of how to get good data from different sources, how to curate it, and how to compact it so it fits alongside with the user prompt in the smaller context windows that we have for LLMs.
Nice. I'm very curious, like the current context window of LLMs is, let's say, between 100K and 1 million tokens. When the LLMs will get more context, let's say, for example, the Llama 4 model has 10 million, will there be less need for RAG since you can put all the things in system prompt?
You still have, it's still RAG. There's still going to be information retrieval. It's just not going to be on the client side. It's going to be in the actual context of the LLM. But regardless of where it is, even with growing context window sizes, we still have seen problems of things like there's a phrase called catastrophic forgetting, where the context it's sometimes so fragmented. Or the topic switches so often in the conversation window that what you end up with in the LLM's KV cache or something like that, it basically creates a complete confusion in terms of systems that do reasoning or try to do a step-by-step reasoning with that data. They typically forget the stuff in the middle. So the beginning of the conversation in the most recent things become kind of rooted as factual data, and the stuff in the middle becomes kind of like a storm of confusion. So.
Why do LLMs consider data in the middle less relevant than data at the start and the end?
Well, it's not so much the position of the data, but it's the way that the systems that we use to compact that data, that summarize the context, compact the context. It seems that in most cases, it happens that it's the stuff in the middle that turns that way, but it's because of the techniques that we use. Yeah.
Nice. I noticed there's a lot of different vector databases. For example, I've used AstroDB. You guys work at Redis, so obviously Redis has a very nice tool for that as well. And I'm curious, what are distinctions between different vector databases And when some of the listeners will be doing RAG, how to approach choosing an actual vector databases and which factors should they consider?
Can I take them? Or we have run some benchmarks against other vector databases as well, and our conclusions was that Redis provided the lowest latency among the main competitors, and also today, if not the most scalable one, it's one of the most scalable ones. So basically, we can scale to 1 billion vectors without penalizing latency, while other solutions or other vector databases that we tested as well. For example, that there was one that with 6 million vectors, it took 6 seconds to retrieve the information that they were looking for. And with Redis, with 1 billion vectors and 90% precision, you can keep a median latency of 200 milliseconds, for example. And with 95% precision, you can keep a median latency of 1.2 seconds, which is super fast when you're doing vector similarity search with 1 billion vectors, because most of the time, we have different algorithms for searching, right? You have flat and you have hierarchical small navigable world. But basically, for the first one, you're kind of doing a brute force, or looking at all the vectors in your database, and that might take a little while. But with the latter, you're not going to look at all of them. So that's why you might lose a little bit of precision, but then there's a trade-off that you gain in performance. Did I say anything wrong?
No.
Yeah.
And another factor here, so for example, you have, when this whole AI push started, there was pure vector databases. So they start, their main data type, it's vectors. And then everything else, it's metadata. The metadata, it's almost like a second-class citizen to those. So it's vector search first and the metadata second. And that is problematic for complex environments, like, in environments that have been around for a long time, like, banking, insurance, things like that. Then you have the traditional SQL databases adding a vector type, which, it works okay, like PG vector in certain cases. But again, it's bolting on something very foreign to a relational database. Now, Redis, it's a remote data dictionary, in we're a key value database. But the advantage that Redis has is that the value could be a lot of different things. But every data type that makes it into Redis as a first-class citizen, it's optimized for that environment. It's optimized for a key value database, for distribution, and for performance, first of all. So vectors are native subfields to our hashes in JSON. We have a search engine or a query engine that basically allows you to search over those very quickly. And we also now have a native vector type called vector sets that it's also almost like as native as strings would be in Redis. So I think combine the best of both worlds. And again, one of the things without vectors, Redis has the advantage that developers, we program against known data structures, hashes, lists, maps, sets. Redis gives you a direct mental translation between your programming language and how the data is stored and managed. So the same commands that you would use with let's say a Java hash map, there's similar commands to do that efficiently on a distributed version of that data structure that you're used to use.
Nice.
Yeah, and I think we can also add something else here, because as Brian said, we're now seeing this emergence of a lot of vector databases, dedicated ones. But those now, they're trying to become like databases, right? They have just emerged, basically, and they don't have the infrastructure, or they don't have the know-how of working with large ecosystems, basically. So Redis has been a cloud database since 2013, something like that. Yeah. So,
yeah, I mean, if you know the Redis story, it's when the NoSQL world exploded, and when the web and the amount of data and the unstructured data exploded, if you had any application that was not performing well enough, they put Redis in between the bad code and the users. So Redis basically it becomes almost like an ointment that cures poor performance, and sometimes gives you enough time to refactor and make things better. But typically, once you start using Redis, you know that it's something that you can live without for specifically for web services, software as a service applications, where the delay to the user and the resources that you can consume if you don't have something like that. If you were serving things straight from, like, say MySQL or an Oracle database, those are expensive queries. So you end up caching. So why not have the cache? It's the surface of attack. It's the surface of action that the users are going to see. That's what we're promoting. That should be the first place you go to, anyways.
Nice. Raphael, I'm curious about, previously you mentioned for vector databases, you have text and then you map it to a vector. How does dimension of vector impact the search results, and how to go about picking specific dimension?
Yes, I think Brian would answer this question better because
So yeah, it really depends. But typically, the larger the vectors are, the more space you're going to take in the database for the vectors, obviously, and the more dimensions you have to compare to basically do things like cosine similarity. Given all those things are typically turn into integer matrix operations, which can be do very fast in parallel with modern CPUs, utilizing all cores, utilizing things like SIMD at the CPU level. So yeah, it matters, but it's not the most important part. The more important part to me, it's the model selection. You can have two models that create the same number of dimensions for your vectors, but that semantically map things differently than other models. So you have to really try all the different models that are applicable to your system, or at least a small subset to basically fine tune how or understand how they work against your data. So.
And since we store information in vector databases, everything is domain specific, right? And then we have to pick for different use cases, different models. Is that true? And
so it really depends. So there's embedding models, and there's things like chat models. So we started calling them chat models, but there's also like reasoning models now that are fine-tuned specifically for tasks, like programming or scheduling shipments in a transportation company. So there's a lot of companies that basically have data scientists working on sometimes taking an existing model and fine-tuning that model for that specific industry and sometimes for that specific company. So we are finding out what we're seeing with a lot of our customers, it's that sometimes a smaller, cheaper, fine-tuned model, it's better than a super powerful LLM like one of the OpenAI LLMs or Anthropic. So,
nice. Yeah. Lastly, Raphael, I would ask you about your tomorrow's talk. I'm very curious. You have a talk on how to get insights about Apollo 11 program using vector search. And spoiler alert, what have you learned about it?
So basically what I do is there's this website called apollorealtime.org. So you can get into this website, and the engineer behind this website who now works for NASA, his name is Ben Feist, and basically he got all the data from 3 different Apollo missions, Apollo 11, 13, and 17, and he synchronized all of this data so we could kind of relive the mission as if we were there back in the time. So if you open the Apollo 11 page, for example, and you click on T-1 minute, it's basically going to take us to 1 minute before the launch of the Saturn V rocket. And then you see all the transcriptions, you're going to listen to the audio, he synchronized photographs, he synchronized videos, right? And he also provided a searching capability that you can search through the transcriptions. But you're talking about here 200 hours of audio. And as a hobbyist or just somebody who's curious and want to learn more about the mission itself, how can I possibly search through all of this data basically, or all of this transcription, if I don't know exactly what I'm looking for? Because if I search for, even there you have the famous quote that is, that's a small step for human, a giant leap for mankind. That's small step for man, a giant leap for mankind. You see, if I had searched for that's a small step for human, I wouldn't be able to come across the information that I was looking for. And if I had searched for something more specifically, like a question such as how did they drink water in space, or how did they go to the restroom in space, or did they do anything wrong, I wouldn't be able to match anything because they didn't say these words exactly. And basically, this is exact keyword matching search. So during the talk, what I'm going to do is I'm going to get all this information, all these transcriptions, we're going to vectorize it, and then you're going to apply some techniques to make this vectorization or the vector similarity search more accurate. And those techniques can be chunking, or in this case, since all the utterances are already very small, we can do the opposite, that is grouping them together, but then summarizing them or extracting information from them so we can improve the accuracy. And then you're going to apply retrieval-augmented generation as well. And finally, we're going to end up with semantic caching so people can learn how to avoid calling the LLM for questions that have been asked before. So that's the talk in a nutshell. And I also tell stories about the Apollo 11 mission. I'm a big fan. I take a Lego model of the Saturn V, which is this size, explain how it works. People love this part. Maybe they love it more than the talk itself.
Yeah. It's a great talk. It's almost like Raphael has the right stuff for it.
I really love the idea and really looking forward to hearing your talk.
Thank you.
Well, thank you very much for your time. At this point, I would like to thank our sponsors, which is Kaldi, Visionect, Human Frog, and Kuffer. And also, I would like to thank all of our sponsors on Patreon enabling this recording. Thank you.
Thank you.
Thank you so much.